Section 240.24b specifies that a grounded conductor must be run from the supply to the service equipment if the utility company provides a grounded conductor. Section 250.24b directs the user to Table 250.66 for the required minimum size of the grounded conductor. The requirement dictates using Table 250.66 for determining the grounded conductor size based on the size of the service entrance conductors. Table 250.66 indicates that a 1/0 AWG conductor is required for 500 kcmil phase conductors. It is important to understand the differences between grounded conductors and grounding electrode conductors. Grounded conductors carry neutral current and provide a path for fault current back to the source. Grounding electrode conductors connect the grounding electrode system to the service equipment. Section 250.66a, b, and c provide specific sizing requirements for grounding electrode conductors, but they do not supersede the requirements of Section 250.24b for the sizing of the grounded conductor for a service entrance. The impedance value of the grounded conductor is an important consideration, especially on the supply side of the service. A larger conductor size such as 1/0 AWG reduces the impedance compared to a smaller size like 2 AWG. Lower impedance is crucial for effectively clearing ground faults and ensuring the proper operation of overcurrent protective devices. Therefore, the grounded conductor for the 400 amp service with 500 kcmil phase conductors should be sized as 1/0 AWG in accordance with Table 250.66. Here are some additional considerations when sizing grounded conductors. Firstly, always refer to the latest edition of the National Electrical Code, also known as NEC, for the most up-to-date requirement. Secondly, consult with a qualified electrical engineer or inspector if you have any doubts or questions about the correct sizing of grounded conductors for a specific application. Thirdly, consider the specific characteristics of the electrical system, such as the presence of nonlinear loads, which can generate harmonic currents that increase the current flowing through the grounded conductor. Fourthly, when sizing the grounded conductor, it's vital to ensure it can safely carry the maximum neutral current that might flow under normal and fault conditions. Fifthly, a conductor with a lower impedance will facilitate a more effective ground fault current return path to the source, aiding in faster tripping of overcurrent protection devices like circuit breakers or fuses. Sixthly, it is important to differentiate between the purposes of the grounded conductor, which is to carry unbalanced load current and fault current back to the source, and the grounding electrode conductor, which connects the electrical system to the earth for stabilization and additional safety. Seventhly, understand that the size of the grounding electrode conductor is dictated by the size of the service entrance conductors, but it is also subject to limitations based on the type of grounding electrodes used. Eighthly, be aware that local amendments to the NEC may exist, so it is crucial to check with local authorities having jurisdiction, also known as AHJ, to ensure compliance with any specific requirements in that area. Ninthly, when multiple services are supplied from a single transformer, the grounded conductor sizing needs to account for the total load served by all services. Tenthly, consider the material of the conductor such as copper or aluminum, as this affects the ampacity and impedance characteristics. 11thly, always ensure that the terminations and connections for the grounded conductor are properly torqued and inspected to maintain a low impedance path. 12thly, when using aluminum conductors, it is essential to use connectors and terminations that are rated for aluminum to prevent corrosion and maintain conductivity. 13thly, the length of the conductor can also affect its impedance, so in longer runs, it may be necessary to upsize the conductor to compensate for voltage drop and impedance. 14thly, regularly inspect the grounded conductor and its connections as part of a routine maintenance program to ensure continued reliability and safety of the electrical system. 15thly, any modifications or changes to the electrical system should be reviewed by a qualified engineer to ensure that the grounded conductor is still appropriately sized and compliant with the current codes. 16thly, documenting the calculations and the basis for selecting the grounded conductor size is crucial for future reference and for demonstrating compliance to inspectors. 17thly, consider using a ground fault protection system, also known as GFPD, which can detect and interrupt ground faults at lower levels than standard overcurrent protection, further enhancing safety. 18thly, understand that NEC provides minimum requirements, and in some cases, it may be prudent to upsize the grounded conductor beyond the minimum requirement to improve system performance and reliability. 19thly, it is also important to be aware that changes in the load characteristics or the addition of new loads can affect the neutral current and may require re-evaluation of the grounded conductor size. 20thly, utilize appropriate tools and equipment for conductor sizing, such as ampacity tables, voltage drop calculators, and impedance charts to ensure accurate and reliable results. The correct sizing of the grounded conductor is critical for safety and proper operation of the electrical system.